Okay, today we're going to talk about section 6.6 in our book, which covers gas laws. So the first thing that we want to go over, and I'm just going to have you read this on your own, you can pause the video, is the kinetic molecular theory of gases, because that's what this section is all about. And we're just going to go over some mathematical equations and some common uses for gas laws. So the first gas law we're going to talk about is Boyle's law. Boyle's law is this equation right here. The P stands for pressure. And pressure in Boyle's law is usually going to be atmospheres, which is abbreviated as ATM, or mmHg, which means millimeters of mercury. The V stands for volume. And the volume is going to be in either milliliters or liters. So those are your common units. Now, as long as both this first pressure and the second pressure have the same unit, either both ATM or both millimeters of mercury, you're fine. And as long as your volume has the same unit, either milliliters or liters, you're fine as well. And you're going to assume that this is at constant temperature. So your temperature is going to be the same. So it's not going to be a factor. If you were to look at a graph of volume over pressure, your volume is going to be on your y-axis. The pressure is going to be on your x-axis. And it would look like this. This is an exponential graph. And that means that this is inversely proportional. So if you notice right here, at this point right here, you have a high volume, but if you look, the pressure is pretty low. If we take another plot point, like let's say one over here, and we look at this one, you've got a very low volume with an increase in pressure. So as your volume is decreasing, your pressure increases, and vice versa. That is an inverse relationship. Okay, one more thing you need to note, and you do not, I repeat, do not need to memorize this for the test. But if you need to convert from atmospheres to millimeters of mercury, here is your conversion. You'll need this on your homework, but again, not on your test. If I give you this if I do a question like this on the test, I would give you the equation. So 1 atmosphere is equal to 760 millimeters of mercury, if you ever need that conversion for Boyle's law. Okay, let's look at our first example question. It says a sample of air occupies 56.7 milliliters at 97.6 atmospheres and 20 degrees Celsius. What volume will the air occupy at 5.89 atmospheres and 20 degrees Celsius? Notice I underlined all of the numbers and the units because we're going to make sure that they correlate with Boyle's law. So let's go ahead and start. The biggest and most important thing in these gas laws, when you have the same types of units on both sides of the equation, so both pressure and both volume, is that your pressure and your volume ones go together and the pressure and volume twos go together. So right here, notice how it says at. These two go together. So these either need to be ones or twos. It doesn't matter which one. Just make sure that you keep it the same. So let's just do ones. So let's just call this V1, and that correlates with this P1 because it says at. And then it says 20 degrees. So that's going to be, again, R1. So that's our temperature 1. Then it says what volume. So we've already used a V1. So this must be a V2. And this is our unknown. We'll occupy the air at 5.89 atmospheres. So this is going to be our P2. And this is going to be our T2. Now remember I mentioned that temperature is constant. Sometimes questions will put in temperature to try to throw you. So notice that the temperature is exactly the same. Well, that means it's constant, so you don't even have to worry about that temperature. Again, sometimes additional information is put in there just to see if you know what you're talking about. So now that we have our V1 and our P1 and our V2 and P2, which are the components of this equation, we're going to go ahead and plug it into this formula. So P1 is 97.6 atmospheres. We're going to multiply that by V1, which is our 56.7 milliliters. And that's going to equal our P2, which is 5.89 atmospheres. Then we'll multiply that by the unknown, which is our V2. So I'm just going to put it in its little variable form. Okay, now all we have is a mathematical equation, and we just have to make sure our units are the same. So our pressure units are both atmospheres. That's good. If it wasn't, we would have to convert and then plug in. And then our unit for volume is milliliters, and over here it's our unknown. It doesn't tell us that we have to have a specific unit for our answer, so we are just fine that way. So now, just the math. We need to get this V2 by itself, so mathematically we're going to do the opposite of what's happening here. So the opposite of multiplication is division. So we're going to divide both sides by this 5.89 atmospheres. And when we do this, it cancels out the pressure on the right side, leaves us with our volume, which is what we want. And over here, atmospheres cancel and leaves us with milliliters, which is our unit that we want in our answer. So now it's just 97.6 times 56.7, all divided by 5.89. And that is going to leave us with 939.54 milliliters as our answer. Okay, now these numbers should make sense. If we take the number that we just got right here and we plug it in for our volume, this side, this 97.6 times 56.7 should equal the 5.89 times the 939.54. Give or take a little bit because we rounded on this answer. So that's how you can tell if you did it right, if you plug back in your unknown. Another thing that makes sense is think about your graph. This is an exponential graph. So your answers should be also exponential. So on this side, our pressure is high, right? We've got a high pressure right here. Our volume should be a low volume because it's inversely proportional. So compare it to the right side. Our pressure is lower compared to the left side, and our volume is way higher, 939 from 56.7. So this makes sense because, again, it's inversely proportional. So that is Boyle's law. Here are some visuals for Boyle's law. If you notice, these are representing volume and pressure. These are this is the pressure applied, these arrows right here. Notice how there's only 2 on this side, and on this picture, I should say, and notice how much volume there is. On the right picture, you've got 4, double the amount of pressure that's being applied on this container, and notice how small the volume area is. So again, this one is showing an increase in pressure, which means that your volume decreases. Over here, your pressure is going to be, lower because you don't have as much force on that, as much pressure, which means your volume is higher. So again, this is showing an inverse relationship. Okay, another example. Oh, just kidding, we don't have another example. Let's go to our second gas law. This is called Charles' law. And Charles' law deals with volume and temperature. So volume, again, needs to be in either milliliter or liter. And then your temperature has to be in Kelvin, always. So your temperature always has to be in Kelvin. If it's not in Kelvin, this problem will not work. So just make sure that your volume is in either milliliter or liter. Just make sure it's the same on both sides of the equation, and that your temperature is in Kelvin. So for this, you need to make sure that you know this equation on how to find temperature. So if it was me, I would just memorize one of them. So for example, I would just memorize this one. Okay, in order to get to a Kelvin temperature, we take Celsius and we just add 273. And the bottom equation is just trying to find Celsius, which you can do mathematically with the top equation. The reason why we use Kelvin in gas laws is because we're dealing with a broader range of a temperature scale, and so remember that Kelvin goes to absolute zero, and that's why we use that in chemistry. Okay, if we were to look at a graph on Charles' law, our volume is going to be on our y, our temperature is on our x, and here is our line. Okay, this is directly proportional, so we're dealing with directly proportional graph. Sometimes this is known as just a straight line graph. And so what this means is that if we choose a plot point on this graph, like right here, okay, notice that the temperature is increasing, but also, our volume is increasing, and also our temperature is increasing. So this is why this is directly proportional. Again, you're going to see that right here with this plot point. Okay, our volume's increasing. Oh, look at that, our temperature increased. So again, directly proportional. So if our volume decreases, that's right, you've got it, then our temperature will decrease as well. Okay, let's show some pictures of Charles' law. Okay, this picture on the left is showing ice. Picture on the right, this is being heated up, a hot plate. So we're adding heat here, and there's ice, and I want you to notice the volume of the balloon. When this started, the volume was the same. So as my temperature is lower here, notice the volume is lower of the balloon. On the opposite side, on the right side, notice that the temperature is higher because this is on a hot plate. Notice the balloon volume. It's a lot larger than the one on the ice. Okay, and that's showing Charles' law. Another example is this lovely little cartoon. You can look at this in a little more detail. Right here, -10. Notice what he's wearing. Notice the balloon. Right here, 0 degrees. Again, notice what he's wearing. Notice the balloon volume. And right there, 10 degrees Celsius. Look at that balloon volume and also what he's wearing. So again, in this picture, as the temperature increased, that volume of that balloon, because we're dealing with a gas, increased as well. Okay, let's now do a problem. Okay, right here, a sample of nitrogen gas occupies a volume of 7.3 liters at 27 degrees Celsius. What volume will this sample occupy at 180 degrees Celsius? Now with Charles' law, you're assuming that pressure is constant. So let's go ahead and underline what we know. We know that we have 7.3 liters, which is a volume, so I'm going to make this a V1, at, notice the at, that means it goes together, at 27 degrees Celsius, which is temperature. What volume, this is our unknown, we've already used a V1, so we're going to make this a V2, will the sample occupy at 180 degrees Celsius? This is going to be our temperature 2, or T2. So now remember Charles' law, you have to have temperature in Kelvin. So we have got to convert. So right here, 27 plus 273 is going to equal 300. So it's going to be 300 Kelvin. So all I'm doing here is just using this lovely little equation, or I should say conversion, from Charles' law. So remember, Kelvin is just Celsius plus 273. That's all I'm doing here. Okay, so this right now is now going to change to 300 Kelvin. And then right here, I'm just going to add 273. So I'm going to get 3, then 15, and then I'm going to get 453 Kelvin. All right, so now that I have all of my variables and the units I need.